The requirements with which the internet was initially built has been changing over time. So initially when the internet was built, there was just the requirement was to send traffic from one static node to another, and with time there was a lot of mobility aspects, and because of let's go over a few examples, and to the top right you can see Facebook's Aquila project, and according to this project Facebook is trying to beam LTE connectivity or internet connectivity to different underdeveloped or developing countries. This is part of the larger internet.org project of Facebook. Google is also trying out something similar. This is the Google Loon project, and according to this project, Google has deployed or trying to deploy a few balloons that can beam in LTE connectivity to different regions, and there has to be a lot of these are mobile nodes that are moving along the edge and providing internet connectivity to different regions. There has to be a lot of communication between these nodes in order to agree upon how to provide coverage. And there has been Netflix has been part of this huge war for net neutrality. And according to this graph, this just says that Netflix peers with certain internet service providers in order to provide data support to particular users. And there has been Netflix, there can be scenarios where it peers with a particular ISP, but its next hop ISP won't be able to route traffic. It won't be ready to route traffic, and it might have to end up peering with that ISP as well. So there has to be a nice strategy for setting up of these peering agreements and for transmitting traffic. And also in the previous scenarios that we discussed, there has to be good communication, and edge awareness helps a lot. And the fourth use case is Eduroam. So there's a lot of roaming going on in current internet. The support for it is less. And Eduroam, according to this project, if a student is a part of a particular university that is a member of this project, he can, as he travels from one university to another, he can just directly connect to the Wi-Fi service available there. So you know that all devices have their capabilities to support multiple interfaces. You can support Wi-Fi and LTE at the same time. But right now, Google is working on one project where it uses either Wi-Fi or LTE in order to gain connectivity to the internet. There are also companies like Scratch Wireless and Republic Wireless that have a similar model in which they use Wi-Fi first, and if the Wi-Fi connectivity is not available, it will fall back to a cellular network and provide connectivity. And because of this, multiple internet access technology is available. There are multiple paths that can be leveraged. So having a global view of the internet topology and gives you a better view of better decision making abilities. And one last example is the scenario where different mobile vehicles can form ad hoc networks and connect to the internet, and as they keep moving, having a better knowledge of how the network is organized gives it upper hand and improves data delivery. So with this, I'd like to just start off with a brief overview of MobilityFirst before we go into the inter-domain routing protocol. So MobilityFirst is a clean state routing protocol, and it was built with one main goal, one main requirement. It was that the number of mobile devices are rapidly increasing, and at some point it will easily outnumber the number of static devices. And for this, the current IP was it had both the locator and the identifiers where the roles were performed by an IP address. But in MobilityFirst, we introduced something called GUID. Over here, we have labeled objects, and these GUIDs are a hash of the public key, and they are assigned to each of these objects. And these objects can be names of devices, persons, they can be contexts, services, or a group of these as well. And we have this GNRS service. So as mobile devices keep moving from one location to another, you can just refer to the GNRS and form the resolution and route packet to the latest attachment point. So you can route based on GUIDs or the network attachment points as well. And two other components, like any other internet protocol, is that there is storage based network layer where there are DTN functionalities being employed, and there is also a reliable transport protocol as well. So before we go to the intra-domain, I'll give you a brief overview of the intra-domain routing protocol in MobilityFirst. Just like OSPF, this is a simple link state based routing protocol, and what they use SETTs and LETTs. So SETT is known as shortest estimated time of transmission, and it is basically an instantaneous time. It is the time taken for a ping to come back, and when it is averaged over a sliding window, you get LETT. And based on the relative values of this, you either do storage or forwarding of packets. This is done on a hop-by-hop basis, and there are temporary storage units where packets get stored, and if the link quality is bad, the packets get stored or they can get forwarded. And there is also a feature of that is provided by GNRS called late binding, according to which these stored packets can be rebinded to the newer attachment point and can be routed towards it. So based on the motivation that we had, the current in BGP routing, in a three-domain routing protocol like BGP, does not provide very good support for edge mobility. It does not provide multipath capabilities. It has multipath capabilities, but it can be provided much more efficiently with the AR. And the intra-domain map of the topology is not exposed that well. It's not exposed by BGP. For supporting all these, we propose AR, which is an intra-domain routing protocol. For implementing AR, we have 5 key components. And for the first component is the aggregation of the internal network topology in terms of aNodes and vLinks. So an AS can be composed of a large number of routers, switches, and basically network components. These can be aggregated into blobs called aNodes, and they can be about hundreds of these components. These aNodes can be an aggregated representation of how these are connected is in terms of this aNode graph. And there are links between these aNodes that characterizes the connectivity between these elements. This information is packetized into packets called network state packets, and these vLinks are characterized by the bandwidth, availability, capability of between aNodes, and they can also be other information such as the type of elements, type of nodes present in an aNode. So in the previous slide, the aggregation process can be done, it's done within an AS. There can be specific border routers that perform this aggregation, and ASes can agree upon some rule to club all the routers. They can club routers based on whether they are late binding capable or whether they are open flow switches. They can be aggregated into an aNode. And they can, and also the amount of aggregation that they do is given to the ASes. It's their decision. And this information is packetized and sent out to other ASes, neighboring ASes. And if you're going to broadcast this, it is going to lead to a lot of overhead, and because of the flooding. And in order to avoid that flood, we use something called telescopic flooding. What we do is that these nSPs are sent at a higher rate to nearby ASes, whereas it is slowed down as the distance in terms of AS hops increases. So for example, if and we tried out a large number of telescopic functions for evaluation purposes, and there are certain parameters A, alpha and beta in these expressions. So A is basically the basic hold time. So if an if an NSP is going to go from one AS to a neighboring AS, that neighboring AS will hold the packet for a certain period of time based on how far it is from the source AS, and then keep broadcasting it. And this alpha and beta are parameters that are hop counts. So based on what is the hop count, the hold time is going to vary based on what function is used. So if you're going to hold these NSPs for a longer period of time, there is this question of staleness. So if there is an AS that is much far away, it is going to have a very stale picture of a particular network organization of an AS that is far away. So in order to get a better picture, in order to route more efficiently, we combine this with late binding. So according to late binding, what we do is we can actually send, if there is a source host L1 that wants to route traffic to L2, it will send the packets towards the edge of the network where it is thinking that the end host is connected to. So after it comes closer to the edge, it will rebind to the newer attachment point. By this technique, we can actually send traffic in the direction where we think it is connected and get good delivery rates. So this is a solution that was proposed for countering the staleness issue that comes up with telescopic flooding. And one last component of EAR is the fast path setup. This is a mechanism that is used for setting up tunnels within domains. So what happens over here is that border router BR1, it sets up a fast path or path from itself to every other border router that is present within the domain, and it sends out a packet known as a path injection packet. So these packets are fast injection packets with L1 and L2 denoting the labels. So as this packet goes out along the path, every intermediate core router will just store an entry in its routing table with the label. So when traffic is transiting through this network, the border router just has to put the label on, and the intermediate routers will just forward the traffic based on the label. And because of this, the intermediate routers will not have to store a lot of tables because for routing inter-domain traffic. And the table size, if you look at it, if there are n border routers, the table size that are present, the tables will be about of the order n squared within in the inter-domain core routers, for the core routers. So this all of this was implemented using the Click modular router software, and one of the key components is that the key features of Click is that you can write modules, and as packet comes in, it flows through these modules in a pipeline manner, and you can easily remove and add your own components. So for implementing the inter-domain routing aspect, we added the NSP handler, inter-domain lookup. There was this logic that we added in for performing inter-domain lookup, and the path injection packet handler that we talked about in the previous slide that does fast path setup, and the on-demand query handler. So this slide basically tells the router decision making process of core and border routers. So in core routers, the decision making is very simple. In both cases, if the traffic is if the destination host is within my AS, we just directly use the intra-domain routing protocol. If in a core router, if the transit flag is set, the router will immediately use the label-based forwarding table, and it will send traffic through. And if it's not set, it will use the intra-domain routing protocol in order to send it to the closest border router that will take care of the rest of the forwarding. In the case of a border router, if the packet is, if the destination is not in my AS, we look at the aNode forwarding table, and if the first aNode, first hop aNode does not belong to my AS, that means that the closest border router is the egress border router in this scenario. So the packet will directly be forwarded to the egress border router based on using normal G-star based forwarding. And in the other case, if it is not the egress border router, it will use label based forwarding in order to send it to the appropriate egress border route. So when we talk about inter-domain routing protocol, we need to mention something about policies, and we had few discussions about what policies are implemented by BGP, what we can support, and what other extra components can be added. So we have this large SID space that can be used for implementing a large number of services. So in our nSPs, if you see, there is a field at the bottom that says the SIDs that are supported within an AS. So if someone wants a particular multicast support, for example, if the SID corresponding to multicasting is set and all the aNodes along the path has this service, you can do multicasting. And other services like Anycast or any other service can be agreed upon based on these SIDs. And one other common policy related question is to answer business relationships. So BGP has all business relationships between ASes. It has peer-to-peer or provider to customer, customer to provider relations. And we can actually implement those relations by tagging vLinks as to whether they are provider to customer, customer to provider, or peer-to-peer links. And based on these business relationships, traffics actually should not follow certain routes. So they cannot. So this is actually a traffic from one peer goes to another peer and then uses the provider of the peer. So such routing cannot happen. You can't use a customer might have two providers. One provider cannot route through the customer to another provider. Such scenarios cannot happen. You can avoid these by tagging the vLinks with provider-customer relationships and routing using that logic in the routing algorithm. So we can also do dynamic traffic engineering by dynamically modifying how the aNodes are formed, how the aNodes are aggregated. And if, for example, if there are a set of aNodes that are congested within a domain, this border router that forms all these aNodes can avoid these aNodes and while broadcasting the next NSP, or it can combine a few of the aNodes in that region and broadcast them as one. Because of this, you can avoid traffic to be routed through these congested regions. And inter-AS agreements for tunnel setup. So we talked about there can be a scenario where there is a company with two branches, and both these branches might want a tunnel setup between them, and there might be a scenario where there are multiple ASes between these branches, and you must agree upon some algorithm or some metric in order to route traffic across these domains. We do that through inter-domain tunnel setup. So what happens over here is there are multiple ASes, and if you want to set up a tunnel between an aNode, say A1 in AS1 and A11 in AS3, the initiating aNode will have to first insert tag. This is basically a GUID, and this GUID will be mapped to the intra-domain tags within the ASes. So AS1 can have a tunnel from A1 to A4 that can have a value of TG1, and A1 to A3 in this case. So it will send a path setup message. So AS1 will take care of setting up tunnel within its domain. So this path setup message will be propagated across domains. So A3 will send it to A7. A7 will again set up a tunnel from A7 to A8, and it will do an EGNRS insert. And this path setup message will be further propagated towards the destination, and there will be another insert mechanism. So there can be it is the role of the initiating border router or the initiating AS to constantly check if all the ASs along this tunnel want to remain a part of the larger inter-domain tunnel. So if someone is not interested in the tunnel, they can just delete their component of the tunnel, and once they do that, TG1 will realize that AS1 will realize that one of the entries mappings is missing in the GNRS, and it can decommission the entire tunnel. So this is just a comparison of what are the different inter-domain protocols that are present in BGP and what are the different policies that are present in BGP and what can be supported by EAR. So local preference is just that if there are two ASes and multiple links from one AS to another, we can select or bias which link is to be selected for traffic, and we can do that by biasing the vLink metrics that are present. And then there is this community attribute. So community attribute is used for enforcing business relationships, and we do have tags for vLinks that can kind of emulate what the community attribute does. And there is a hot potato routing algorithm. For this, we can simply set an SID, and if that SID is set, you can just route traffic based on AS hop-out. And for load balancing, you can always do dynamic aggregation that we talked about while the nSPs are formed. For scalability, there are these three components. There is prefix aggregation. So prefix aggregation cannot be done in EAR because we cannot aggregate multiple nSPs that were received from different ASs and broadcast them. There are a few papers like AIP, which is Accountable Internet Protocol, in which they do experiments, and in one such experiment they actually broadcast multiple address blocks that are segments of a larger block, and an edge network broadcasts these blocks, and you find that in the end these blocks don't end up getting aggregated. So there is not much of prefix aggregation that is happening in today's internet, is what they try to say. And because of that, we feel that there is not too much of an impact of not having NSP aggregation capabilities. And we can always use default routes. And for route flap dampening, which might happen if some link keeps fluctuating, you can modify the telescopic timers, flooding durations, in order to control this. And the global roaming, blacklisting, and network initiated control can be achieved in AAR by using the GNRS or SIDs. So let's just look at two simple scenarios of how data gets routed in case of AAR, and we'll just be looking at what tables are used. So if the source is in AS1 and destination is in AS2, the only two border routers involved in this scenario are R2 and R3, and there will be an intra-domain routing decision making that will happen at R2. So when source sends packets to R1, R1 will use the G star forwarding table and send the packet to the closest border router, which is R2 in this case. R2 will use the aNode forwarding table and send it to its neighboring border router, which is an inter-domain border router, to R3. Since R3 and R7 are within the same domain, after that all the tables that are used are G star forwarding tables. So you have two alternate paths, and either one of the paths can be used based on the link metrics within the domain. And the other scenario is AS1 routes packets to AS3, and in this case AS2 becomes a transit AS, and we talked about setting up of fast paths, and it is in these transit AS that fast paths will be used. So AS1, just like the previous scenario, you send packets to the closest border router. As soon as it goes to the egress border router, you will use the tunnel. So the fast path table will be used on all the intermediate core routers in the transit domain, and it will go to the A8 will make an inter-domain routing decision and send it to R9. R8 will make the decision, send it to R9, and after that it's again intra-domain routing. So we did a few evaluations in order to test the scalability, feasibility of our protocol, and we also tried out, evaluated a couple of use cases. And the first evaluation is we tried out multiple telescopic functions. We first took a 200 node topology from, we emulated a 200 node topology from DIMES. We used the link latencies given there, And for this topology, we try to find out how much time it takes for all the nodes to learn about a particular update, NSP update. So we found that it is just the constant exponential. The constant exponential constant performs well along with constant linear telescopic functions, and it's just that the constant exponential and the exponential telescopic functions that cause the updates to take long time to get propagated. So since these three do well, we want to evaluate the overhead that gets generated. Since it takes very less time for these packets to get delivered, but this might lead to a larger flood. So we evaluate, we tried all these with parameters 5, 2 and 4 for A, alpha and beta for the telescopic functions. And we evaluated the overhead and the settling time for the constant exponential constant telescopic function. So in this experiment, we actually took AS topologies of about 47,000 ASes with 200,000 vLinks, 200,000 intra-domain links. And we tried to see, so we actually see a particular region of A, alpha and beta values that resulted in a low overhead that is less than about 20 Gbps and settling time of less than 2000 seconds. And we can actually tweak these, reduce the values of A in order to get better performances in certain regions of the internet. One thing that was observed was that the current internet traffic is about 172 terabytes per second, and compared to that, these values of about 10 Gbps is peanuts. So one of the observations that we can do over here is that these green, purple and red lines are actually stand for A, alpha, beta of 6, 10, 12 with A value of 6 to n 12 and alpha value of 2. So alpha is set as 2 and the value of A is 6, 8, 10 and 12. So what happens is, up till the second hop you hold the packets for 8 seconds or 6 seconds, and after that for 2 more hops you do telescopic hold, and beyond that there is again constant hold that happens.
Can you contrast that a bit with what happens in BGP?
This one? In BGP, the updates, announcements are sent, but one thing that happens is there is aggregation of these announcements that happens. You can aggregate some of these announcements that go through, and it is not flooded across the network. So we know that BGP is scalable because it is not flooded. So we wanted to evaluate how this is going to perform because of the flooding.
Why can you not aggregate?
One key thing is that we can't aggregate it because of the nSPs. The ASes have complete control of how the nSPs are generated. So if there is a particular ASP and it gives a particular AS that gives out a particular topology of aNodes and how they are connected through vLinks, and there is a second AS. You can't combine the two. The second AS cannot combine information from the first AS and broadcast it out. So that might lead to duplication of information. So since the first AS will already have, say it is going to send it out every 10 seconds, the second AS might also do the same thing. And if you're going to aggregate the information, in the end it's going to, the same size packet is going to go out every 10 seconds. So aggregation is not going to play.
Wait, the same size packet goes out every 10 seconds?
So if the size of the NSP generated at AS1 is k bytes and it is k2 bytes when it's generated by AS2, if you add them both, aggregate them both, it's just going to be k1 plus k2. It's not, and there may be a little bit header size reduction. You can't reduce the size by aggregation as such. So in BGP, the aggregation that you do will lead to reduction in the amount of prefixes that you will broadcast announce a prefix that encompasses two other announcements. You can't do one such
So what's the
approach.
fundamental difference that makes it possible in BGP yet not possible here?
So the fundamental difference is that it is flat over here. In BGP, since it's hierarchical, you can easily do perform the aggregation. But because it is flat, you won't be able to aggregate them.
So if you were to compare BGP numbers with these, it might be worthwhile to roughly estimate that. So BGP, a typical exchange between a pair of BGP nodes is what in your, do you know that value? Roughly speaking, in internet route, for your gateway router, how many bytes does it send to its neighbors?
So it is.
So my impression
Order
is
of
that's of the order
less
of 10
than
megabytes
MBs,
per
yeah.
transfer. I mean, it could be more or less. Then if you multiply by the number of inter-domain links, then you can get a comparable estimate. Should
But
be of one order of magnitude less at least.
Yeah. If you reduce the timers, the value will increase in the case of BGP. But along the edge, if we want to have better knowledge of how the network is organized, we will have lower timers. If BGP does the same, even its value will.
Do you think the setting time is one order of magnitude less? Or?
No, the settling time would be much higher. I think it's been calculated to be in tens of minutes. Hours. Depends on the
BGP.
the repetition.
So here you're at 1,000 seconds.
Yeah.
How many minutes is that? It's about
20 minutes.
20 minutes.
We can actually take lower values of. So there are certain values of A, alpha, beta that leads.
So you can pay a slightly higher price. It's not obvious that, I mean, the curve looks nice for selecting parameter, but you can go up.
Yeah, we can take certain values that will give us a lower settling time. One other evaluation that we did for testing feasibility was the routing table size. So in EAR, the table size is basically the number of aNodes that are present across the internet. So since you can't do any kind of aggregation, so the tables are going to be equal to the number of aNodes. So what we did over here is that we changed the fraction of aggregation. By fraction of aggregation, what we mean is that, so if the fraction of aggregation is 0, it means that every router that is present within a domain is going to be an aNode in itself. And if it is 1, all the routers will be part of one single aNode. So an AS is an aNode. So we took a distribution and we took each of these fractions as the mean with a Gaussian curve and a variance of 0.1, and selected randomly for every AS. We selected a random number and did aggregation of the number of routers present within that AS, and we found values to vary from 10 to the 10 power 5 to much lower values. We found that it was about 400,000, that there are about 400,000 entries in the case of a BGP interdomain routing table, routers table. And if you do aggregation at about 60% aggregation, then you will actually, we get very comparable table sizes in the case of EAR.
What is the definition of fraction of aggregation? Remind me.
So we basically defined, it is used to define the number of routers that become part of a particular aNode. So here it is inversely proportional
So
to
0.6 would mean about 2 aNodes.
Yeah, 0.5 means that every 2 aNodes are part of an AS, of an aNode. Every 2 routers are part of an aNode. So we did evaluation of 2 use cases, and the first use case is an end-host mobility scenario. So what we tried for this, we actually developed a mobility matrix, and using this mobility matrix, it is a probabilistic approach where we, using the mobility matrix, we generated a set of transitions, And what we do over here is we try to route traffic to a particular end host, and as the end host moves from one location to another, the GNRS is updated. So there is a late binding point or some point in the network where the resolution or late binding happens and traffic gets rerouted to the new destination. So we actually consider two kinds of mobility in this. There is this micro and macro mobility. By micro mobility, what we mean is that there is a high chance of traversing and attaching to a particular access point within the same AS inside a radius of certain distance r. And macro mobility is that there are about Z over here, network transitions, interdomain transitions that are allowed. And if you are going to consider large mobilities, if none of these close-ranged access points are selected, the larger, farther ones will be selected. And we actually try to find the path stretch for this data transmission. So path stretch, what path stretch is if you consider a particular node and try routing traffic to that node, it is basically the ratio of number of hops to that node with the shortest path to the node. So if you are trying to reach a particular node, if it is 7 hops through a particular path, and there could be a 3 hop shortest path to that node. So it is 7 by 3 is the path stretch in that scenario. So we tried doing that for this case, and we found that using late binding has a significant impact and reduction in path stretch. And large portion, large amount of traffic was routed with path stretches of less than 1.3, whereas without late binding there were segments that were delivered at there was a lot of rerouting that happened. And the last use case was for network mobility. So for network mobility, what we did was that we considered a bus, for example, that moved from one location to another. And as it moved, this bus itself was considered as an aNode. So as it moves, it goes and attaches to different ASes and becomes part of that AS. So in the nSP that gets generated by AS5 after this mobility event, aNode A44 will be part of that nSP. So when traffic gets routed to a particular destination, say aNode 44, to a destination within aNode 44, it will fail at some point because it will try to route it to this domain, but this domain would not have any content, it would not have this aNode, and it will have to be rerouted. So this transmission will happen more accurately after the nSP from AS5 goes through. So that is highly dependent on the telescopic hold time parameters. So we wanted to show how the telescopic hold times affects routing of traffic when network mobility happens.
What would be the motivation for representing the bus as an aNode?
So network mobility is the motivation. So we consider a set of nodes or mobile nodes that are moving at the same time. So we have a lot of phones that connect to the Wi-Fi of service of a bus, which can again connect to a particular network. So that bus in that case is a collection of users connected to it. So
but you're saying you want to do a network mobility, so you come up with an arbitrary scenario where you have some network mobility. Shouldn't it be the other way around, that you come up with a scenario where there's an advantage if you have network mobility?
So we have this network mobility use cases happening in many places, and we wanted to try out how it benefits when we use AAR.
So my question is, you have many phones in a bus using the internet right now, and there's no aNode for the bus right now.
The bus itself.
Right. So if we're sitting in a bus playing with our phones right now, we're all accessing the internet. So what's the advantage once you introduce an aNode?
So
what can I do that I cannot do today?
So once you send it out, broadcast this information as an aNode, you don't have to worry about how traffic gets routed to me. So there can be a border router within the network that will take care of how traffic gets routed to the bus and hence to me. I don't have to, the bus doesn't have to worry anymore. It can just be any other router that connects to the network through vLink, and the inter-domain routing protocol will take care of sending traffic. So there can be just one border router within the domain that will add it to the inter-domain routing table and send traffic efficiently.
Certain I follow that thing.
So AS6 can have some border router, arbitrary border router. So once aNode 44 forms is present, it will become a part of the inter-domain routing table. So AS6 will have a border router, and the border router will have aNode 44 as an element in the inter-domain routing table. So it is the inter-domain routing protocol will take care of how to forward traffic to aNode 44. So there is no more requirement for the router present in the aNode as well. So you just need to connect to the internet, and the inter-domain routing protocol
So
will
you're
take
saying
care.
the bus doesn't need to have a router?
What is it?
The bus does not have to have a router anymore.
It will have a router, and if it can be a border router, and if it is a border router, it will just add the elements. It will have to learn about the inter-domain nodes. So it will just have to know about the first AS. If it has that information, it can immediately route traffic. It's neighboring AS information. It will be able to route traffic. But with time, it will learn about all the aNodes present in the other ASes as well.
So I mentioned that there is a scalability advantage here, that if you have 100 people in a network and the network moves, instead of having 100 signaling messages to update the GNRS, you don't have to do anything. The GNRS remains unchanged, but the routing layer takes care of the transition. So it's more of a scalability argument. But I think you can also answer him in terms of connecting to Wi-Fi. That's a different reason.
Okay, why don't you go on?
So in this experiment, we actually considered a number of routes or bus traces within San Francisco, and as the buses move along one of these routes, we just were observing the loss rate, or the number of chunks that were dropped with respect to the number of chunks that were sent when data gets transmitted. So one of the observations, this is basically the result that was obtained through the experiment. That is an observation from the data set that we used. We observed that if an aNode moves from one being attached to one AS to another, the number of hops between the original and the destination ASs was distributed this way, and it was found that there were a large of 2 hop transitions. And if you see this graph, this is basically the value A over here is the value of A in the telescopic hold time functions. So these show that if you increase the value of A, it takes a longer time for the nSP to reach all the ASs, and hence there is a bit more increase in the loss rate. Whereas for the first graph, it shows that it's almost constant. So this is because most of the transitions that happened in that particular route were single hop AS transitions. So because of that, there was not too much of an impact of telescopic hold time, and because of that, we were able to see almost constant, almost very similar or comparable loss rates in this experiment. So after this, I'd like to conclude that we were able to design and implement an inter-domain routing protocol on click, and we evaluated the feasibility of this protocol in terms of control overhead, convergence, and table sizes. And we also tried out and evaluated 2 use cases. One is the end-host mobility and the edge network mobility. For future work, we'd like to start using the GNRS a bit more and try to implement some services that becomes easier to implement when GNRS is present. And use cases like multi-homing and Anycast service need to be evaluated, and they can also be compared with existing or proposed inter-domain routing protocols. That's it. Have any questions?
Can you state again what property makes your routing protocol edge aware?
So, by edge aware, so it's basically the same scenario, the network mobility use case. We are trying to show the organization of the networks along the edge. So by giving this information, if you consider use cases like multicast support and multi-network connection. So for example, if a mobile device has multiple interfaces, Wi-Fi and WiMAX, or Wi-Fi and cellular at the same time, having an awareness of how or what link it is using to connect along the edge will improve data delivery. So the Boeing example is one other scenario where if you know what is the link, there is a wireless link between the ground device and the plane, and if you know that beforehand, you can throttle the amount of traffic being sent and improve data delivery. So knowing such information is very beneficial to improve.
And where exactly is that represented right now in your protocol?
So in our protocol, we have that vLink, and that vLink can have metrics. So right now we are giving availability, bandwidth, and variability, and these links can be tagged with characteristics such as it being Wi-Fi capable, it being a Wi-Fi link, wireless link, or the node being having specific characteristics like late binding capable or storage capable aNodes.
And you have these only for the links at the edge, or for any link?
It is present for any link, but it makes more sense to make proper decisions at the edge. It is useful at the edge as well. The motivation was.
So at some level it's not with any link aware network.
So to answer his question correctly, so if you have, what can you do now that you cannot, what can you do with this that you cannot do now? You have a bus, and the bus is charging $2 extra for Wi-Fi connectivity, and so he's giving, with EIR connecting the bus can offer you a full-fledged cellular quality service, or maybe even better than cellular quality, with the network taking care of all of the mobility. The bus all of a sudden became magically a mobile network, which otherwise would have to have $50 subscriptions using up their data allocation. The mobility logic is now taken care entirely by the network.
You don't need this other system.
Yeah, in the limiting case, so opportunistic access, many other features are there, but you have to answer those. Okay.
So are you able to actually predict where this bus is going to connect and have the packets wait before they even arrive?
We haven't used a prediction algorithm for this evaluation, but we generated a set of transition points. So we did not do any kind of prediction beforehand. So it is basically the GNRS has, once the event happens, only then the GNRS gets updated. And only after it happens do we do rerouting of traffic to the new destination.
Okay, when you say it happens, means the reassociation happens.
Yeah, reassociation. Okay.
So you haven't done that kind of
We don't
optimization.
So you could mention that if you have, because these things have ETN logic, there is some element of prediction built in. That's part of the G-star protocol, but they haven't actually extended it to the EIR.
Yeah, I think Thesis has done something very similar in the setting, but he was doing content prefetching.
Use Markov models.
Right.
But the DTN has some, like there is a metric that looks at the probability of something being there at any given hop, and so how do you estimate this? That's the same as trajectory estimations. questions from the audience? It's your last chance to ask. I think he's out of Rutgers by Monday.
I have a question about the calculation of the routing table size. Can you explain a bit more about how did you calculate the comparison with the BGP?
Yeah. So you saw that there was a factor we call the aggregation fraction.
Yeah.
So what that does is, if the value of aggregation fraction is 0, it means that every router present is considered as an aNode. And if that value is 100, it means that all the routers get considered as one single aNode. So one AS is one aNode. So we have a estimate of how many routers are present in each AS. So using that, we actually take a distribution, and if with a mean, for example, at 0.5 and a variance at 0.1, and from that distribution we take an aggregation percentage factor and try to find out the number of aNodes that are present within a particular AS. So the number of, it is inversely proportional. We use that and find the aggregation percentage, find the number of aNodes. And it's just the sum of the number of aNodes present in every AS, that is the table size. And for BGP, we got the value from Qaeda.
So does DPIR use the aggregation as a built-in service?
Aggregation, in the sense, it just aggregates routers into aNodes, and it is left to the discretion of the ASes. They can decide upon how to aggregate it.
So if I aggregate more, do I lose information about the edge of the network?
Yeah, you lose information in terms of, you lose granularity information, and there can be ISPs that don't want to expose any information about how their internal network is organized. They might aggregate everything into just one.
So but we do think that generally ISPs will benefit from exposing some structure, but the structure they expose may have very little relationship to their physical network. They just want you to pick certain paths. The difficulty now is in a inter-domain routing, ingress and egress is done in a very clumsy way because you don't know what's inside. So you could go in, AT&T has a global network, but you could go in at the opposite end to go out from some direction. You have no control over that. So if AT&T exposed some kind of a double tree or something, they could get you to select appropriate paths coming in and out of the network. So that would be a benefit to AT&T. But they don't have to show you where the data center is or something. Ivan just came in, so you ask him a question.
No, I'm not gonna scare him. Some stress-free last few minutes, right?
Okay then, thanks. So give us the paperwork and we can thank you.